Okay, so in these slides we want to derive or understand the fundamental theorem of calculus. But before we do that, the first thing you need to do is to review the mean value theorem. And there's a video before this one that has a review of the mean value theorem. So you have to do that before you continue. So let's say you have a function f of x is 2x and the function g of x is x squared. And these two functions actually are special in a certain way that the derivative of g of x with respect to x is just f of x. So basically just one is the derivative of the other one. So, and you can see that clearly, x squared, when you take the derivative, it becomes 2x. So these are the two functions we have. And in the coming slides, I'm going to ask you just to follow what I'm doing in each slide and try to see where we're heading. I'm not going to say where we're heading. Maybe typically I would say we're going to do this and that. No, I'm just going to do a few derivations each slide, and I want you to try to figure out where we're going with this. So let's take any 2 points on the function g, this one and this one for instance. They could be any 2 points. And let's make a line between the 2 points. And then let's calculate the slope of the line. So the slope of the line is this distance minus this distance, which gives us this part here, and then divided by this distance, which is x2 minus x1, and that will give you the slope of this line between the 2 points. Okay, the mean value theorem, and that's why you have to review it very well to understand what we're saying now. The mean value theorem says that there must be a point x equal to c, somewhere between x1 and x2, such that if you take the derivative of g at that point, c, the derivative will equal to the slope of this line. And you can actually see it visually, that this black line and this red line, they have the same slope. And so the mean value theorem just guarantees that this will always happen. You'll always find the value of c such that the derivative of g at some point will always be equal to the slope of this line, joining the two endpoints. Okay. If you rearrange the terms a little bit, you get that the value of the function at 1.2 minus the value of the function at 0.4 is the derivative of the function at c, as we said, times x2 minus x1. Okay, but what is g prime of c? G prime of c, we know that the derivative of g is f. So g prime of c is basically the value of the function f at c, the value of this function evaluated at c. And so if you look at what that means graphically, if you look at the value of the function f at c, it's basically this distance. And if you look at x2 minus x1, it's basically this distance. And so basically graphically, what does this right-hand side mean? It means the area that's shown here in red. And so we just found that the value of the function g at the end point minus the value of the function g at the beginning point, the difference in the value of the function g is just related to this area right here. Now this area doesn't seem very interesting, and there's nothing particularly great about it. It doesn't look that useful, this result. But again, let's continue. And as I said, just follow what we're doing from each slide to the next and think where we're heading with this. So let's apply the mean value theorem at two different intervals. Let's go from 1.2 to 0.8. And then we'll go from 1.2, to 0.8 here, and then from 0.8 to 0.4. So we have these two intervals. This is one interval, and this is another interval right here. And so if you apply the mean value theorem to each interval, in this region, you'll have to find the value of c1, such that if you get the value of the function at c1 times this distance, it should equal to g at 0.8 minus g at 0.4. And the same thing applies for the other interval. You'll find the value of c such that the value of the function at c2 times this distance will equal to the value of the function at 1.2 minus 0.8. Okay, that's fine. Again, still nothing really great we've done here. Let's add. let's add the two terms. If you add the two terms, you'll notice that this will just cancel, because when you add something with the same value and opposite sign, they just cancel. So you just get the endpoints. So you just get exactly the same left-hand side as we had before. But now look at the right-hand side. You have two terms. You've cut up your interval into two terms. You have the value of the function at C1 times this, the value of the function at C2 times that. What does this represent graphically? What does this part represent graphically? It represents exactly these two rectangles in red, because the value of f at C1 is this value, is this distance, times this gives you this area, and then the value of C2 is this distance, f at C2, times this distance gives you this area. So you get now the difference in the value of g at the endpoints equals to two terms, two areas. And the areas are related to the function f, not the function g. Okay, we can rewrite this just slightly. Instead of saying x2 minus x1 or x3 minus x2, let's just call it delta x1 to represent this distance and delta x2 to represent this distance. Nothing changed here. And let's then apply it to four intervals. Let's take between 1.2 and 1, and then from 1 to 0.8, and then from 0.8 to 0.6, and then 0.6 to 0.4. Do the same thing. We don't have to repeat what's going on here. I think you can get from what we did before, what we just did just now. Okay, let's add again. Now if you add, look what will cancel. The G1 with the G1, the 0.8 with the 0.8, the 0.6 with the 0.6. And you're left with also the value of G at the endpoints, at 1.2 and 0.4. And now you have four terms. What do these four terms represent graphically? They represent areas. Which areas? The ones right here. Okay, that's great. What if we keep on doing this further? So let's cut this interval into 20 parts. So we did summation from 1 to 20, the value of the function at certain points in each interval, times delta xi. And the delta xi's, by the way, they don't have to be equal. There's nothing we did so far that says they have to be equal, but let's just keep them equal for now. And still, this sum should equal to the difference in the value of g at the endpoints. Now this, you can see where we're heading now. It should be clear. I think it should be clear what this area, what this part in red represents. It represents the area under the curve f between 0.4 and 1.2. And so little by little, as we add more intervals, we're approaching the area under the curve f between the endpoints. Okay, what if we let n, the number of terms, go to infinity? Still, the mean value theorem will always guarantee that we'll find certain values of c in each interval, even though they're infinite intervals, but they will always guarantee to find a value of c in each interval such that this sum is equal to the difference in the value of g at the two endpoints. Now this, once you let n go to infinity, now this becomes exactly equal to the area under the graph of f of x between 0.4 and 1.2. And so this is the very important final result of what we're trying to show. If you take the difference in the value of a function g between 2 points, this is the same thing as the area under the derivative of g between the same 2 points. And this is represented, this area under the curve is represented as a definite integral. This is just a shorthand notation that they use. Instead of saying it's the limit of sums, you can write it this way. It's integration from 0.4, this shows the endpoints, 0.4 to 1.2, integration of f of x dx. You just plug in here the value of the function, which is 2x, and that will give you the difference in the value of the function g between two endpoints. So this is the fundamental theorem of calculus applied to our example, where we took a function f of x is 2x and g of x is x squared. This is the way it would be stated for our particular example. But as you can see, and I think you can see very clearly that this derivation didn't really depend on anything at all about g being a certain function and f being a certain function. And the only important thing is that the function f is the derivative of g. And so the general formulation then of the fundamental theorem of calculus, if you apply it to any function g and any function f, such that the derivative of g is f, any two functions that satisfy this relationship, and of course they have to, because of the mean value theorem, take the g has to be continuous and differentiable, of course, so it has to take all the properties that come from the mean value theorem. Then the integration from a to b, the endpoints a to b, of f of x dx is equal to the value of the function g at the endpoints, this difference in the value of g at the endpoints. And this integration is basically just this limit of sums. And now instead of saying n goes to infinity, we can say delta x goes to 0. The value of each interval goes to 0, tends to 0. It's the same thing. And as we said before, the partitions don't have to be the same size. And this is just basically the area under the curve. So we found that the area under the curve between a and b is just equal to the value of the function g at the endpoint b minus the value of the function g at the endpoint a.